85% of the matter in our universe is a mystery. We don't know what it's made of, which is why we call it dark matter. But we know it's out there because we can observe its gravitational attraction on galaxies and other celestial objects. We've yet to directly observe dark matter, but scientists theorize that we may actually be able to create it in the most powerful particle collider in the world. That's the 27-kilometer-long Large Hadron Collider, or LHC, in Geneva, Switzerland. So how would that work? In the LHC, two proton beams move in opposite directions and are accelerated to near the speed of light. At 4 collision points, the beams cross and protons smash into each other. Protons are made of much smaller components called quarks and gluons. In most ordinary collisions, the two protons pass through each other without any significant outcome. However, in about 1 in a million collisions, two components hit each other so violently that most of the collision energy is set free, producing thousands of new particles. It's only in these collisions that very massive particles, like the theorized dark matter, can be produced. The collision points are surrounded by detectors containing about 100 million sensors. Like huge three-dimensional cameras, they gather information on those new particles, including their trajectory, electrical charge, and energy. Once processed, the computers can depict a collision as an image. Each line is the path of a different particle, and different types of particles are color-coded. Data from the detectors allows scientists to determine what each of these particles is, things like photons and electrons. Now, the detectors take snapshots of about 1 billion of these collisions per second to find signs of extremely rare, massive particles. To add to the difficulty, the particles we're looking for may be unstable and decay into more familiar particles before reaching the sensors. Take, for example, the Higgs boson, a long-theorized particle that wasn't observed until 2012. The odds of a given collision producing a Higgs boson are about 1 in 10 billion, and it only lasts for a tiny fraction of a second before decaying. But scientists developed theoretical models to tell them what to look for. For the Higgs, they thought it would sometimes decay into 2 photons. So they first examined only the high-energy events that included 2 photons. But there's a problem here. There are innumerable particle interactions that can produce 2 random photons. So how do you separate out the Higgs from everything else? The answer is mass. The information gathered by the detectors allows the scientists to go a step back and determine the mass of whatever it was that produced 2 photons. They put that mass value into a graph and then repeat the process for all events with 2 photons. The vast majority of these events are just random photon observations, what scientists call background events. But when a Higgs boson is produced and decays into 2 photons, the mass always comes out to be the same. Therefore, the telltale sign of the Higgs boson would be a little bump sitting on top of the background. It takes billions of observations before a bump like this can appear, and it's only considered a meaningful result if that bump becomes significantly higher than the background. In the case of the Higgs boson, the scientists at the LHC announced their groundbreaking result when there was only a 1 in 3 million chance this bump could have appeared by a statistical fluke. So back to the dark matter. If the LHC's proton beams have enough energy to produce it, that's probably an even rarer occurrence than the Higgs boson. So it takes quadrillions of collisions, combined with theoretical models, to even start to look. That's what the LHC is currently doing. By generating a mountain of data, we're hoping to find more tiny bumps in graphs that will provide evidence for yet unknown particles like dark matter. Or maybe what we'll find won't be dark matter, but something else that would reshape our understanding of how the universe works entirely. That's part of the fun at this point. We have no idea what we're going to find. Every TED-Ed video you've seen is the result of many months of hard work from people all over the world. For example, this quirky video about particle physics was a collaboration between the TED-Ed team, a scientist at CERN, a handful of script editors in New York, and an animator in the UK. And now, after 5 months of creative collisions, the video exists. And it's free for you and everyone else in the world to learn from, and to share forever. As our channel grows, we'd love to take on bigger and bolder collaborations. But TED-Ed is a nonprofit, so we can't do that without a little extra help. So if you enjoy TED-Ed videos, please help us make more of them by supporting our work on patreon.com/TEDEd. As always, thanks for watching.